Today, I'd like to share a little bit about our journey into distributed tracing and how we've leveraged OpenTelemetry. My name is Chris Detsicas, and I'm an SRE in the internal observability SRE team at ThousandEyes. We build and maintain the internal observability platform to empower our hundreds of engineers with insights about service health and performance. So we all know it. Today, our applications, our people, our infrastructure are all distributed. Gone are the days of that single server monolith. Our requests will take paths through many different technologies, SaaS platforms, and even different cloud providers. At ThousandEyes, we build a network assurance platform to help customers visualize, understand, and detect problems in their own networks and the internet. And this provides customers with deep and actionable visibility across any network. So, of course, it's imperative that we can understand what's happening beneath our platform. If we have a problem, customers may not know that they have a problem. And over time, we grew. The company expanded, we delivered more and more services to our customers, and requests would take many different paths throughout our infrastructure. Internally, we're keen on observability, but we wanted to go a bit further with distributed tracing. So let's take a quick peek at the agenda. First off, I'll give you an overview of our platform and perspective of our services that we have involved. Then we'll look at troubleshooting without distributed tracing for one of our flows and the challenges that this presented. Then we'll peek at the difference that distributed tracing can make there, before we touch on the topic of context propagation and provide an overview of our solution with OpenTelemetry. And then finally, I'll cover the challenges of adoption for distributed tracing. Okay, so what kind of services are we talking about here? So at a high level, ThousandEyes collects network telemetry data from agents all around the world. Some of these agents are run by ourselves, what we call our cloud agents, and some by our customers. They're constantly running tests against customer targets. This is collecting things like BGP routing data, network performance metrics, DNS, HTTP performance data, and more specialist data from tests such as web transaction and voice. Data is submitted to our ingress services, and then our pipelines transform and enrich this data and store it for longer-term consumption. And then we have a plethora of business and data services. This is where we got tons of services, and this will provide insights and data to our customers. Some customers even send data further through our streaming services. So it's actually possible to export our network metrics as OpenTelemetry data as well. Many customers will consume data via our detailed web UI and our API, or they'll receive alerts when we detect problems. Beneath the many services are hundreds of engineers and many teams. There's a touch of complexity to deal with here. So in terms of technologies, what do we have? We've got a bunch of Java, and a lot of Java in fact, with some Kotlin, some Go, some C++, Python, and even some Rust. We're predominantly deployed upon AWS using Kubernetes over 3 core regions and some disaster recovery regions. We're big users of Kafka for moving data, and we store our data in a number of data stores, including MySQL, ClickHouse, Elasticsearch, and MongoDB. These services communicate with each other in the outside world with Istio, our service mesh. And shout outs to our wider SRE team who performed a major migration across clusters using Istio. It gave us benefits including the gRPC load balancing, the general service discovery abilities. We can also do some network traffic modification, network policies, but it also gave us a ton more additional observability. In fact, we kind of killed Prometheus at first. We had so many metrics, so we had to tone down the labels. But this did give us aggregated metrics on service health and usage, and cluster-wide access logs. So we started to gain a better understanding of which services interact with each other. So in fact, here's a little graph that shows the interconnections between services from the namespace housing our web application. This is generated by Kiali, a UI that provides used to visualize Istio service meshes. As you can see, it looks somewhat chaotic, right? There's lots of moving parts and services interconnected. Imagine what it's like when trying to debug problems. There's 2 services interconnected, but can we really tell under which circumstances or for which requests or user operations? So we were conscious of the distributed tracing features in Istio, but hadn't yet explored it. And that was just one motivation to start a journey into distributed tracing features. So next I want to take a look at our troubleshooting flows before distributed tracing with one scenario. So imagine it's early morning, pager goes off. We're all familiar with that one, right? So customer requests are receiving elevated numbers of 5xx errors, and we load up our computer to inspect the metrics. Let's figure out what's going on. Okay, great, we see the drop. We know something is wrong serving these web requests, and we can see it's trending down. However, we don't really have much context. Metrics are great for identifying trends and alerting us towards a problem, but lack that deep context. So next, the responder following a runbook may start looking at logs. Okay, there is an excerpt of some access logs. This is quite useful in the case of an availability issue. Great, we know which endpoints are failing, but which services are downstream of this? Is there a single agent view service? Is there a scheduled test service that has a problem? Is there a timeline service? And why is this really a 500? At this point, the responder is going to go check further dashboards, logs, and try to build up those mental pictures. They're going to consume a lot of information that isn't directly related to the requests involved. They may try to determine ownership of the services in the request flow and can contact additional responders. This is quite difficult, and it's going to be quite frustrating. So to summarize the challenges involved. First off, we got the manual correlation. You're trolling through many dashboards, you've got 300 graphs on one dashboard, looking for that anomaly, looking for the spikes and the dips, trying to build up those mental hypotheses for failure and the request path for problem requests. Tricky, time-consuming, and might be going down the wrong path with lots of red herrings. And then there's lack of context. Our logs are really high volume, and you get that needle in the haystack issue. Unless they're particularly verbose, they tend to lack the context on request flow. And metrics are really aggregated. There's no granular detail on the specifics of a problem. If there is, maybe you have those high cardinality issues. And then responders will struggle to identify really what services are involved behind a request. And then you've got tribal knowledge. We all know that one guy who's always available, he wrote the service, he knows it inside out, and what happens when he's not around. As we grew our teams and reorganized, this was only going to become more of a challenge. We can't rely upon luck here. And then people fatigue. Responders going through the same kind of alerts, same kind of flow often, struggling to resolve it. They're only going to get tired with this. And another side effect of this is we can pull the wrong people into incidents under suspicion that their service is involved without being able to confirm it. And this will distract them from building new features for our customers. And overall, all of these factors contribute to slower resolution of problems and incidents. So now what does troubleshooting look like once we have distributed tracing in the mix? We'll look at the same scenario. So we've got those same access logs, but now we have trace IDs added as well. And this is actually something we've done. We made sure that the signals are mixed, and it really helps people find the traces. So let's take a look under the hood of these exact requests. Okay, great. There's a lot of information right there. We can see first off that requests started at our ingress controller. Great, we kind of knew that from our logs, right? But we can also see it passed through our API gateway, various Istio proxies intercepted the request, and eventually landed up at the agent view service. Now we even see that we're calling the data access scheduled test service. And this seems to be where the problem lies. So let's dig in a little further to that span, get timeline data for metrics method. Okay, taking a little look further, we can see that we've got an exception there. We can even open that up. We've even got the full stack trace, but it kind of got hidden. Thanks for a sec. So now the team had a ton more information than the initial access logs. They could pinpoint the issue occurs when test data is not found. In this case, they were able to determine the UI was still making erroneous calls for test data, even when a test is disabled. They were able to mitigate this with a pull request to update the UI, and then later update the backend to ensure that the test not found results in a 404 at the API as well. We did have exceptions through other means of our error reporting tools, but with the trace, we're able to go straight from the log all the way through to the end-to-end flow, which services are involved, and see the exception in context. So now I want to touch on the concept of context propagation, because this is pretty key to distributed tracing in general. So let's give some context on context propagation. So first service in a request flow has to start a span context object. It will determine a trace ID, and then it will determine a span ID for its own operations. There won't be any parent span ID for the root service. There'd also tend to be a sampling decision here as well. And when the service A makes a request to service B, it's going to inject the headers. In the case of HTTP, that's HTTP headers. Service B will extract and start its own span context object. And that will identify the parent span ID from service A. And then it will create new span IDs and new span context objects for its own operations. And so on. Same for service C. As we can see, the trace ID was maintained throughout. The parent span ID maintained the link between spans throughout this trace. This is super important to maintain order and composition of traces. Spans will come far and wide throughout our infrastructure. And the sampling decision is also there. That's typically passed along with the context. First service makes the decision in most cases with head sampling. There's more elaborate sampling strategies out there, but we'll keep it simple for now. So what were our typical request flows like, and how would we go about maintaining this context? Would we have to update code across all of our applications? Let's first take a look at a typical request flow among our services. So it's a similar scenario to what we showed before. The user is requesting test data for an agent. First, the request is going to arrive at our Nginx ingress controller via an Istio proxy. We've got Istio, our service mesh, intercepting all requests inbound and outbound. And then that's going to call our agent view service before arriving at our data access service. That's going to call some other services and databases to service the request, but we keep the diagram simple. So Istio is intercepting all requests, right? At first, we naively wondered, could we get traces out of our applications and understand these request flows by just enabling tracing in Istio without changing our application code to propagate context? And we often get this question when we're encouraging tracing. Can't Istio just do this for us? Unfortunately not. So you could do something like this. A request arrives at our Nginx ingress controller. Istio starts a trace. Span context object is created with trace ID. Unfortunately, Nginx is going to pass on those headers to the next service. So the Istio proxy in the agent view service will receive the request, extract the trace context from the ingress controller. The agent view application will then make a request to the data access service. But unless it includes the trace context headers, Istio is going to start a new trace. Unfortunately, Istio is not psychic. Without changing our code, we'd end up with disconnected traces. So that would look something like this. We have one trace for the first part of the request flow, the ingress controller and the agent view. And when agent view makes a request out to the data access service, this trace unfortunately gets broken, unless it passes on headers to propagate context. Not ideal, right? I said the problem was manual correlation. So we'd need to keep traces connected. We'd have to figure out how to keep context propagated throughout both our applications and our infrastructure components, like Istio and Nginx. This is where OpenTelemetry came to the forefront. How could we build a tracing pipeline and instrument our applications to maintain that all-important context? So let's start looking into OpenTelemetry. Before we go into our pipeline in detail, I'll first introduce OpenTelemetry for those who don't know. Here's a very relevant XKCD comic. It's known in tech throughout, very prevalent, right? So distributed tracing was relatively proprietary end-to-end before OpenTelemetry arrived on the scene. There was no consistent trace format or protocol shared among vendors. Vendor X, if you wanted to move from vendor X to vendor Y, you'd have to strip out instrumentation in your code and replace it with new instrumentation. That's pretty time-intensive work when you could be spending that building new features. And so OpenTelemetry arrived, and we got this framework for vendor-neutral instrumentation, collection, and export of telemetry. It provides a set of APIs, SDKs, and tools to instrument, generate, collect, and export logs, traces, and metrics. And there's also some exciting new work on events and profiles, which we're following closely. And there's a standardized format, OpenTelemetry Line Protocol, or OTLP for short. But ingestion and export of many formats is supported. And that was a fact that particularly piqued our interests. How are we going to collect all the data, though? Well, in steps the Swiss Army knife of the OpenTelemetry world, the OpenTelemetry collector. It provides a vendor-agnostic solution for collection, processing, and export of OTel signals. So with this, we could receive telemetry in different formats. For us, that meant OTLP and Zipkin. We had assessed our infrastructure, and at the time, Istio did not support the OpenTelemetry format, although this has since grown and it's recently even gained HTTP support, and we'll have to see about moving there. So we configured our collector with both OTLP and Zipkin, and this allowed us to collect OTLP spans from our OTel agents in our code, and Zipkin for our infrastructure components such as Istio and Nginx. And then we could export to multiple backends as well. So when we were first starting, we were just trying out many different backends. With the OTel collector, we could make sure that the same traces actually ended up in various different backends, and we could compare literally the same trace side by side. So we assessed them on factors such as user interface, search and query language flexibility, and API integrations. And then in terms of our deployment method for the OTel collector, one method you can use is agent mode, where you sidecar it against your application. The other method is to put it centralized in your cluster in gateway mode. We decided to put it centrally because that meant that we wouldn't have to restart or reconfigure all applications when we change config variables, such as changing the tracing backend or parameters on the tracing backend. But it also meant we could centrally filter spans. We could add resource attributes such as environment level details via a resource processor as well. And if we were to move towards tail sampling in the future, we'd already be deployed centrally so we could filter everything out. So how do we deploy this collector? Well, here's the next bright idea. Especially if you're operating in Kubernetes, this can be particularly useful. It's the OpenTelemetry Kubernetes operator. So we use this to, number one, manage our OTel collectors. There's an OpenTelemetry collector custom resource. And we define our receiver, our processor, and our exporter config here. And then this deploys multiple replicas of the OTel collector behind a Kubernetes service, and even does things such as managing auto-scaling via HPA. This is a really quick way to get OTel collectors up and running. But the real magic really came in with the injected auto-instrumentation. So to propagate that all-important context and get rich telemetry out of our applications, we were going to need instrumentation. And with this, we define an instrumentation resource, and that injects OTel environment variables into pods and allows us to define agent config in a custom resource per service. So upon service startup, an init container is injected into the pod. This pulls the OTel Java agent and also injects it into the service at startup. And this meant teams could get a really decent level of instrumentation without even adding the library to their code directly. So what does that instrumentation resource look like? Well, it's a little like this. So those with keen eyes will notice that our propagators are actually both trace context and B3 multi. So our Zipkin-based infrastructure, Istio and Nginx, was going to need that B3 multi format to be able to propagate the headers throughout. So while we'd send traces in both formats, we needed to configure the OTel agents to not only propagate trace context for future, but also Zipkin's B3 multi format to support Istio and Nginx in this case. And then we also use the Kubernetes object metadata to build some of the OTel environment variables, in particular the service name, to match it to Istio's service name and keep things consistent. Otherwise, we'd end up with variations of each service name and essentially duplicates. The instrumentation will also add a ton of environment variables with Kubernetes-related metadata to the pod at startup. This includes things like pod name, namespace, node name, and this is particularly useful for troubleshooting and correlating with logs and metrics, or to look at things like specific pods and their traces coming from that pod. So what did the overall architecture look like? So we've got that same request flow, and requests are arriving at our ingress controller. Istio starts a trace context, sends a request to the agent view service, and the context is included as B3 multi-headers. The agent view service makes a request to the data access service, also sending a trace context as B3 multi. The trace spans from Nginx and the Istio proxies are in Zipkin format. The OTel agent in the applications, the instrumentation added with that injected instrumentation, is OTLP. But because we're using B3 multi throughout to keep trace context and trace ID the same, the propagation isn't broken and our traces remain connected. So everything gets transformed at the OTel collector into OTLP, and then it's exported to our backend, Grafana Tempo currently. If you're diving into tracing, what you may find is you've got older software and infrastructure that doesn't support these latest OTLP and W3C standards. But the good thing is the OTel collector likely supports the standard that you need and will convert it to OTLP. There's support from many different vendors and formats out there. So the next challenge, once we got our pipeline up and running, was going to be adoption, and how do we encourage usage of this? But when I think about adoption, there's sort of two sides to the story. Services need to be instrumented, so we get that all-important context propagation, and detail on service operations. And that needs to be as easy as possible. But then there's also people side of things. They need to start using the system once we've got that data in place. So we were conscious of the two main types of instrumentation, automatic and manual instrumentation. With the automatic instrumentation agents from OpenTelemetry, they would provide instrumentation agents for a whole range of languages. This will natively instrument applications with common functions such as HTTP, RPC, database, and messaging calls when common libraries are used. This will also ensure context propagation when these operations transit multiple services. Most of our services are Java, and they could quickly benefit from the auto instrumentation. And then there's manual instrumentation. With manual instrumentation, engineers will add the OTel APIs or SDKs to their code, and then they would need to manually extract and inject the tracing headers using those SDKs and create spans for their code operations. This will provide us with more flexibility and a bit more detail perhaps, but had those development time hurdles. Ultimately, some of our services using C++, Go, Rust had to use this, but we wanted to focus on the auto instrumentation to start with. And then I'd mentioned that injected auto instrumentation, but this is really where we lent in. We could add that OTel Java agent to a service in a matter of minutes and get value really quickly from tracing. This is probably the main method used for instrumentation, and currently like 100 plus services instrumented in this way. So how are we going to encourage instrumentation once we've got those options? Well, first off, we focused on a core service, our main web application. We added the injected auto instrumentation to our application, our web app and our API with our web platform team. And this gave us that core example that was recognized across the organization. Many people have used everyone's used the main ThousandEyes web UI, and many have actually contributed to it as well. And this would help us to encourage tracing in other applications. One team had actually 50 plus services, all in Java in a mono repo. And with some clever customized patching, we were able to instrument all of their services relatively quickly. And then there's rich documentation. We have a pretty global organization at ThousandEyes, and it's important that engineers could instrument their code and get up to grips with distributed tracing asynchronously. So this documentation explained our pipeline architecture, gave us detailed instructions on instrumentation with references out to the OpenTelemetry docs, and it had the copy-paste and self-service examples to instrument services with the operator. And that injected also instrumentation. And then tech talks. At ThousandEyes, we've got a pretty good tech talk culture. This allows engineers to share just interesting tech they found, new product features and how they built it, and also platform changes like this one. Once we had that core example, like the web application, we had some demos available. We could show this to the rest of the org. And we had the documentation to refer to so that people could get started. So we wrote a tech talk, and we delivered a tech talk covering distributed tracing generally, how does the pipeline work, and how to instrument your services, with a focus on that injected auto instrumentation. This provoked a lot of questions. Some really enthusiastic teams got to instrumenting their services right away. And then there's production readiness checklists. It was always going to be harder to get old code changed and instrumented, but we didn't want to increase technical debt further. So we added a mandate for instrumentation to our production readiness checklists. Okay, so once we get all that data in, people need to start using the system to really get insights from it. So one of the things we did here, and there's multiple areas, once we had that core example updated, the web application, we updated the runbooks for our web application. And this really gave responders that reminder that traces exists, especially in the heat of the moment. In an incident, they may forget, but it also had the tailored queries, so that if they didn't know the query language yet, it helps them understand it and find things like the 500s or the high latency, and they just click in the link, and then it's front and center to them, and they'll remember it. And then there's mixing signals. So old habits die hard. Responders that are used to checking their logs probably going to still focus on their logs. So we added trace IDs into Istio and Nginx access logs from day one. And the OTel Java agent also generally adds the trace IDs into logs. And many users we found will jump straight from logs to traces. They see a trace ID in the log and they think, okay, let me see what's going on underneath that. And then there was a generic trace explorer dashboard. So we were conscious that people may take some time to learn the query language. We wanted people to be able to quickly explore traces involving their application as soon as they've instrumented it. So with the dashboard, they could go and they could click on their service, and it will run through some queries such as find the high latency traces, find those with errors, and then find some with lots of spans because they tend to be more interesting. That allowed people to immediately explore the tooling once instrumented, and they could use the queries as examples to build their own. And then there's incident game days. So one of the things we do at ThousandEyes to train new incident responders is we run simulated incidents. And some of these scenarios we use tracing, and the runbooks, the same ones with the web application, and that help people get used to the observability tooling. If it's actually not used in a response, we can go to it afterwards in the debrief and help people get familiar. It's easier to mold with fresh faces, and if they see the value from it, hopefully use it more often. And then just generally evangelizing for tracing, thinking, can we solve this with tracing, or helping out people in incidents? So my team and myself will keep an eye on live problems sometimes. And if we see a problem that we think maybe can help with tracing, or maybe it's something with the web application, we'll go and help people build queries and just give those little reminders. We've even added auto instrumentation into a service mid-incident before. Another weird use case we actually had was Jenkins. One team had particularly slow builds, and they couldn't quite work out why. It was running lots of parallel branches and lots of steps. But we added tracing to Jenkins. They could visualize the whole build as a trace and immediately see what was taking the most long. And it turned out it was reading an external file. It was taking about 1 to 2 minutes extra. They embedded the file in the Jenkins job, and they immediately got that 1 to 2 minutes back per build. So, next off, that's driving usage and our adoption, but our journey isn't really over yet. Of course, with many things in tech, you've got to keep it maintained, and we've got more to do. So here's just some ideas for the future. We're still relatively new to distributed tracing, so we still need to instrument more services. Adoption is growing, but there's still lurkers out there. And one of the benefits that we got with Istio intercepting all requests is that we can track which services are not instrumented. We'll need to put some focus on those. And next, exemplars. I've mentioned trace IDs in the logs, and one of the key avenues that our users use is the jump from logs out to the traces. However, it would be even better if we could use exemplars. With exemplars, we'll be able to have data points on our graphs. So say that availability drop graph, have a data point there, you click on that, and then you could see exact context, an example scenario, or an example trace of why that availability drop is happening and that 500. So imagine looking at that and how quickly you could jump from your alert to a full context. And then there's more. OpenTelemetry in the front end. Our digital experiences are more and more in the browser now, more and more going on with the user interactions with JavaScript. And we've been exploring adding tracing capabilities to elements of our front end to really understand the user experience all the way from the browser out to the back-end calls. And then there's some advanced sampling strategies. So right now we sample at 100% in our staging environments, which is great for debugging pre-release and even reproducing issues. But we're mostly at 1% in production. That's keeping the volume low. Most of the time this is okay, but sometimes we don't get enough data, or we miss requests. And we're still keeping a lot of data that isn't interesting. For example, lots and lots of successful interactions. So what we want to explore is tail sampling and sample at 100% on the client end, and then collect all traces in our collector, and then make decisions such as sample traces that contain errors at 100% or a little bit lower, sample those at high latency, or even sample those some with specific operations at a higher percentage. Okay, so quick recap. So what we need to recognize really is that system and organizational complexity will continue to grow. Our observability tooling can help overcome this. We can keep evolving the tooling to break down hurdles in troubleshooting. And distributed tracing is one way that's proving effective for us to help resolve problems faster. But we couldn't have done it without OpenTelemetry. Or at least the journey would have been a lot tougher and less future-proof. The standout features for us were really the ability to integrate multiple standards, test out multiple backends, and ultimately switch in the future with relative ease. And in terms of adoption, there's of course always going to be a hurdle, but what we found helps is to make it as easy as possible. Lower that barrier to adoption with detailed docs so that people can do it asynchronously, and the tech talks help to do it a bit live sometimes, and encourage the adoption and get people excited about it. The injected auto instrumentation was really the lifesaver there, though. It really helped us get teams up and running quickly and get that instrumentation into their code. And of course, in terms of getting people to use the system, just try and put the tracing in front of people through runbooks, give them little reminders, and running and mixing signals like adding trace IDs in their logs. So make sure they come across it when they're looking for other signals so they can jump straight from those logs out to the traces. Okay, we got there. All right, if anyone wants to find out more about ThousandEyes itself, please visit our LinkedIn or feel free to ping me directly. And if anyone is interested in joining ThousandEyes, please check out our career portal to find out about careers. We are recruiting SREs as well. We've got a booth out in the sponsor showcase, so please come and say hello. And finally, our journey with OpenTelemetry isn't just internal. We also produce it by incorporating OpenTelemetry into our product. On Thursday at 3:10, my colleague Antonio from the streaming team will be exploring how HTTP archive files can be transformed into OTel traces and used to understand the user experience in the browser. Thanks for listening, everyone.